All right. So I was just at the dentist this morning, and it was at like 8 a.m. And I was like, it will have worn off by the time it is not worn off. So um, he likes went crazy with the meeting. Anyway, so. Last two little chapters, and these are both pretty quick, like this one's only 4 pages. Before the final. So, Amy. So formally, these are derivatives of ammonia. Ammonia is H3. And so if we take ammonia and start substituting the hydrogens for R groups, we can get something like this. So we substitute one groups, this becomes primary amine. With two R groups, so this is in H2, this is secondary. And we keep going. And R3. Is the tertiary. You can actually go a step further. And do that. Now there's no lone pair anymore on the nitrogen. And it's going to have a positive charge. So this is an R4 plus.
Pretty much demanded.
And this is ordinary ammonium salt because ammonium is NH4 plus. So amines have two different sort of ways that they react. The first is we can act as bases. So we have ammonia and then an acid like HCl. You can just deprotonate the acid, or you could do this with carboxylic acid. That's what happens in amino acids. And so we get well, this is just NH4. And or amines can act as nucleophiles. So instead of HCl, let's use chloromethane, something like that. And so arrows here are going to look the same, but in this case, it's being considered a nucleophile because we're making bond to the carbon and not hydrogen. And so in this particular case, this is an activation reaction. But we're going to come back to alkylations more in a second because they're a little more complicated than just what I've shown there. Okay, we haven't really talked about the geometry of really any of the functional groups that we've discussed, and that may not necessarily be a good thing, but and amines have three groups, whether they be hydrogens or R groups or something like that, and also a lone pair on the nitrogen, so the quaternary ammonium salt being an exception. And so if we remember from Vesper theory and Gen Chem, when we have something like this, the molecular geometry is trigonal pyramidal. And the nitrogen atom is sp3 hybridized. So when we have an sp3 hybridized carbon and all of the groups are different on the carbon atom, we call that chiral. So the same kind of goes for nitrogen atoms. If we have these three groups all different, and you could say in the same way that carbon has to have four different groups, well, the lone pair is sort of a group, if you will. But anyway, for the R groups here, if you have three different groups are present, the molecule will be chiral at the nitrogen. So there's one example where we have three different R groups. But we can also draw another molecule with the same connectivity of atoms that is not equivalent, because nitrogen is chiral, and so the asterisk means it's chiral. And so those two molecules are enantiomers of each other. sometimes it doesn't end up mattering because you can actually go back and forth between those two. So if you give it some heat, basically you can flip between the two. So let's see what that looks like. If we have amine that looks like that, currently the R groups are bent to the right. Go through sp2 hybridized intermediate, which is achiral. So at this point, everything is in this plane. One's going straight up, one's coming forward, one's going back. So we bent everything from the left up, and now we can bend things over to the right. And again, this is sp3. And it's chiral. So, for example, if this happens to be the R enantiomer, this is going to be the S enantiomer. That's where equilibrium pairs will be back. Yes.
So does this imply that the amine temporarily has 5 electron pairs?
No, so these, this hybrid orbital is empty at this point. And the electrons, basically what happens is the electrons are in sort of, that lone pair is kind of spread out in the bonds here. Oh, that sounds kind of weird.
So it's like when we put benzene, there would be like a bunch of dots.
Yeah, I wouldn't draw it like that, but that's kind of the same idea.
So it still fills up then.
Yeah. So there is an energy barrier that you have to get over in order to go through this sp2 hybridized intermediate. And it's about 25 kilocalories per mole. Actually, kind of a lot. And it depends on the specific amine, exactly how much, like in the lab, how much heat you have to give it in order to do this. But that process can So fortunately, this is going to be actually a good bit of review. Because we've already done like several different ways to make amines. You can start from an alkyl halide like this to introduce our nitrogen. We can substitute with cyanide. And then if we treat the nitrile with lithium aluminum hydride, we keep this carbon here, the nitrile, that will come to this carbon. And in this case, we get a primary amine. Another way to get primary amines carboxylic acids. This is a bit more roundabout, but you take a carboxylic acid, if we treat it with thionyl chloride, we get to the acid chloride. Now we introduce the nitrogen with ammonia. That gets us to the amide. And from there, we can use lithium aluminum hydride to get rid of carbonyl. And we get to, again, in this case, a primary amine. We can also do electrophilic aromatic substitution. So, we'll call chapter 18 and put a nitro group on an aromatic ring with nitric acid. And of course, if you have something on the benzene ring to start with, you have to take into account the orthometic para-directing functionality. And then from here, really the easiest way to do this, and we didn't talk about this in that chapter, is just to hydrogenate. So using hydrogen gas and then a palladium catalyst of some kind. And that gets us to the NH2, and because we have an aromatic ring next to it, we call it an aryl amine.
Dr. Eubanks,
Yeah,
doesn't this mean that you have chapter 22 on the exam?
kind of. Just to tell you. Okay, but now this is stuff we've not talked about. You can use those methods. There's another one which is actually even worse, but I'll show you why it's worse. Alkylation of ammonia. So as I said at the beginning, you can treat amines like ammonia as nucleophiles. So if we have, for example, methyl iodide, this is just an SN2 reaction. To get that salt, and then after workup, just going to write it as ethylamine. You breaking bad fans? Anchor car with ethylamine. Yeah. So this is H2. So you could say, all right, well, now we can pick any alkyl group we want and just do this alkylation process. Problem is that substituted amines like methylamine are stronger nucleophiles. They're more nucleophilic than ammonia. So if we still have methyl iodide in the reaction, which you're going to have some, the product of the reaction is going to react faster with the reagent than the intended starting material. So what ends up happening there's our first reaction. Ammonia and methyl iodide give us methylamine, which is now a stronger nucleophile than ammonia. So it reacts again. And we make dimethylamine. And guess what? Dimethylamine is an even stronger nucleophile than methyl. See where this is going? Dimethylamine. And then it actually happens again. To the point where we get tetramethyl ammonium. And then the counter ion is iodide. So you can't say, okay, I'm just going to do 2 of these alkylation steps and end up with dimethylamine. You could even say, okay, I'm going to make sure to only add 2 equivalents of methyl iodide. That way we only do these 2 reactions, right? No, you're going to get a whole mess of products. Some of the molecules are going to react first, become stronger nucleophiles, react again, and so you're going to end up with mostly this plus a lot of starting material left over. So this is not a good way to make anything except this. Now, these are useful. They're kind of like soaps because let's say we've got, I think it's octal, something like that, but I don't know, I'm just gonna draw a bunch of carbons. Something like that with a bunch of carbons. One of them is a methyl group, I know that for sure. And then I think the counter ion is fluoride. This is a really common surfactant. So it's polar because it's ionic, right? And it's nonpolar because it's got these long alkyl groups. So what you can do is, if you've got a reaction that you're trying to do in two phases, you can stir and get those two phases to interact, or you could drop in a little bit of this and it'll cause the two layers to combine. It's kind of sorcery. Then you have to work up everything and separate everything, which that's a whole other nightmare. But so for something like this, a process like that could be useful, but not usually. Okay, two more methods. Next is azides. So if we take an alkyl halide and react it with NaN3, kind of weird. This is sodium azide, which is, of course, Na+, and then the azide ion is that. It should look sort of cursed, and it is. It's explosive and it's pretty toxic as well. If you count the charges here, sodium azide itself is neutral. We've got two positive charges and two negative charges. The azide ion is also written as N3- because ignoring the sodium, you've got one positive charge and two negative charges. That totals -1. Okay, so what does this do when we react it with an alkyl halide? Well, we do a substitution. This is just, again, an SN2 reaction. And we get an organic azide, where we treated it just like a regular ion with a minus charge, and we just form a bond here, and the rest of the azide is the same. So this is Rn3. And then we can do a reduction with hydrogen and palladium catalysts, And that reduces off the azide group and just gives us primary amine. So for example, if we take that alkyl halide, react it with sodium azide, we just substitute bromine for N3, and you can just abbreviate it N3. You don't have to throw out the whole thing unless you want to. It's kind of fun. And then H2 and PD, hydrogenation conditions. This gives us the amine. So the alkylation process in the middle there is not super useful because you can't stop in the middle. So what happens when we want to make a partially alkylated amine where we've got, be a methyl group or whatever organic group, or two methyl groups or two different organic, like how do we make these really sort of specific amines where we can pick each of the groups that's on the nitrogen? And that's done with reductive amination. So if we start with carbonyl compound, we can get away from them that easy. Sorry. We start from a carbonyl compound and we treat it with acid, and we use ammonia as an example, but we can swap that for other things. We get as an intermediate. And imine. You can isolate this. There's other ways to make amines that are better than this. But really what you do here is hydrogenate the imine. And that gives us an amine. So I've drawn out this hydrogen to show that one of the hydrogens from the hydrogenation goes onto the nitrogen, and one of them goes onto the carbonyl carbon. Hence why it's called reductive amination, because you're reducing the carbonyl. So the ammonia here, this can be primary or a secondary amine. Tertiary does not work for this though, but that's okay because if we want to make a tertiary amine, we can, well, we've already got one group that ends up being attached to the nitrogen, so that can be our third group. So what does this look like? Okay, cyclohexanone. Cyclohexanone with acid and methylamine. And then, right, hydrogenation. So this is an abbreviated way of writing these two steps here. So like we did with carbonyl chemistry, sort of is carbonyl chemistry. See, now we're not done with chapter 20. See, this is still chapter. Sorry. So we draw everything except the reactive center, so everything except the carbonyl. And now what do we do? Well, we're going to reduce this atom. So it's going to have only single bonds to it now. And what's going to be attached to it? Well, everything that we added in this step, just minus a hydrogen. So in this case, that means the nitrogen with its methyl group and a hydrogen.
That Eubanks.
Yep.
So we can kind of think of it almost like a Grignard's reaction, where like we have a car on it and BBR, it's just kind of like popping. As it like replaces the carbonyl.
Kind of. Of course, with a Grignard, you end up with your thing attached and then an alcohol, which is not the case here. I guess, yeah. So what about this one? This one. Now the numbing has worn off, but my mouth hurts. I don't know which I think I'd rather have my mouth hurt a little bit. Any volunteers? Yeah.
All three of them, or just one?
Oh, I mean, I'm sticking just one, but somebody else, come on. Okay, let Alex do this. I think do this one first. Okay. That's no, it's okay. It's okay. All right. So we replace the carbonyl with single bond to our nitrogen and everything that's attached to it minus the hydrogen. So that's two methyl groups. So we get two methyl groups attached to the nitrogen. Benzaldehyde. It's an aldehyde, so the hydrogen's just going to stay there and act like it was this group on the other one. So we replace the carbonyl with a single bond, the nitrogen, and everything that's attached to it minus the hydrogen. So that's going to be the benzene ring and an additional hydrogen. This one, replace the carbonyl with a single, okay, hold on, probably a second. Single bond to a nitrogen, and everything that's attached to it minus a hydrogen. So in this case, subtracting a hydrogen is going to leave us with no more hydrogen. And a ring like that. Same thing. Question on that? Have the exams if you would like them. Deb, can I kick you out? Oh, and I have a bunch of other stuff. Actually, don't go too fast because I have your stuff minus here. I'm going to leave the exams up here. And